So thanks for having me today. I will present a paper titled Dynamical Isometry is achieved in residual neural networks in a universal way for any activation function. And I hope by the end you will more or less know what I mean by this long phrase. And this was done in collaboration with two of our friends from the Mathematics Institute here. And this paper was just presented at AI Stats 2 weeks ago. But first, I will allow myself to make a short introduction to neural networks and deep learning. There are, I guess, only 2 or 3 other talks touching upon these subjects at this conference. So this is a simple neural network. You input your data points here. The numbers go and are summed up in nodes in some hidden layer, and the sum is subject to an activation function, and then goes again to another layer within an output. Okay, and you adjust the weights that you sum your inputs from the previous layers with, and this way the network learns what answer it should give to a given question. And these questions can be quite diverse. So as you will know, you can tackle both classification and regression questions in a supervised setting like this, or in an unsupervised setting, for example, with autoregressive networks. But the real fun starts when you add the number of hidden layers. And this is, when you do that, this is called deep learning. And what we will talk about today here at my presentations will be really deep neural networks. So why this deep learning is so powerful and works so well? So traditionally in machine learning, your data scientist would take the input data and would perform expert knowledge-based manual feature extractions, and those features would be then put into a machine learning algorithm, which would, in this case, for example, answer the question whether on a picture there is a car or there is no car. What deep learning allows is to skip this first part, and because there is so many layers and so many things, so much can happen with the input data, you can perform this task by just, for example, inputting the picture itself. But of course, the problem with that is if you want to tackle complex questions, you need to have a lot of freedom in your network, in your algorithm, right? But that means a lot of parameters. So there is a lot of weights that you need to adjust. But that also comes with a problem, because if you have a lot of parameters and not so much of the data, you can over-parameterize easily. And this is something John von Neumann said at one point, that with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk, you know. So with a lot of parameters, it's very easy to overfit, and actually it was shown in 2010 that with 5 complex parameters you can draw an elephant like this. And of course, those state-of-the-art deep neural networks that are used today can have millions or even billions of parameters. So, so the deepness helps, right? The fact that you have many layers and they're wide, it helps, but there is a fundamental problem with that, and it's one of the open questions to some extent in deep learning. Okay. So this is it. So you have massive over-parameterization. So why don't these neural networks overfit? But there are other major areas of research, and some of them are technical, right? So what functions or what activation functions I should use for my particular problem? How to train to be efficient, not to waste resources. How to choose the architecture of a neural networks, right? Because these were the models I showed were really simple. You had basically a constant number of neurons throughout the layers. And one particular such question is how to initialize those neural networks, right? Because you can imagine that if you start with the weights being 0, right, no information will go through the network to start the learning process, and you will have no way to train it because there will be no feedback. Okay? So this particular question we will tackle a little bit. So we tackle a little bit in this paper I present. Of course, there are other questions. For example, that are more practical. For example, the question of explainability. Right? If I have a deep neural network and it does some complicated algebra when it attempts to answer a question, then I might want to ask, what was the reason that, for example, this part of the image was categorized as containing, for example, tumor in some high probability, right? And there is the question of robustness, and by that I mean that current neural networks are easily fooled. So you can add some noise to an image and make a perfectly nice and efficient and accurate neural network make really easy, stupid mistakes that a human wouldn't. Okay, but let's come back to the main topic now, the initialization of neural networks. So what precisely I will be speaking about, I will talk about initialization of deep residual neural networks, or at least this is the result I want to present, and how we tackle this problem with the help of random matrix theory and free probability theory. Okay, and to make a short summary of the contribution, we do that by looking at an object that is called the input-output Jacobian of a neural network, which I will introduce later. And the point will be that wherever the singular values of this matrix are concentrated around 1, then the network will be able to learn efficiently, basically irrespectively of the depth. Okay? One thing I didn't mention is that, and it's something that you can imagine, that the deeper the networks, because there are more parameters, and there is, let's say, a longer way between the input and the output, so the harder the network a priori should be to train. Okay, but the message is that if the singular values of this Jacobian are concentrated around 1, then we have something called dynamical isometry, and the network learns irrespectively of the depth. Okay. Before we go further, let me explain what is a residual neural network. So the residual neural networks have just one additional feature, namely skip connections. So when you have the input to a given layer, let's say here, the sound inputs go through the activation function, but additionally, when they go to yet another layer, there is the input from the previous layer added to that. And this is motivated by the fact that perhaps we want to allow the network to have it easier to represent identity, as information travels through it. Okay? So now I will state this problem of initialization in more details. I will talk about what was done earlier for feedforward neural networks, and then I will tell you what we found for resonance for those types of networks. Okay. So let me be a little bit more precise. Now this is how my signal in the network will propagate along the layers L. The layers will consist of n neurons and will be large, and there will be L number of layers here, and L also will be very big. Okay, and here this is called the post-activation in layer L. This is the activation function which acts on the pre-activations. These are vectors, so the elements of the vectors are just the numbers associated with the neurons within a given layer L, and the pre-activations are what you get out of taking the inputs from the previous layer and acting on them with multiplying them by the weights here. Okay. And of course, you have to start from something, right? So the easiest choice, the most natural choice, is to start, because what you do, you adjust the weights, right, during training. The easiest choice is to start with the weights being random. Okay. But the question is, if you want to be as efficient as possible, or we want even the learning to be able to occur, what should be, how should we initialize more precisely those matrices? And you can see the problem up close here when you ask the question, how learning occurs. Okay, and it occurs basically by adjusting the weights proportionally to the gradient of the cost function in this for this task. And if you expand this derivative, what you get is the following sum. You get the derivative of the cost function with respect to the output layer. You have a term which tells you how the output layer changes with respect to the post activations in layer L, and you have a term telling you how the post activations in layer L change when you change the weights here. Okay, and the most problematic term in this sum, the one that either may make your weights jump too far, okay, so the adjustments be too big in such a way that you jump out of some valley, for example, in this complex hyperplane, okay, or they can be too small so that you don't move at all during learning. The one that gives you the problems here when the network is really large is this term, and it's in its most extreme version. It's the derivative between the last layer and the input layer, and this is what it's called the input-output Jacobian. Okay, so now the idea is to tame this object. And you can tame it by looking at and its singular values. Okay? And if you write it as a matrix, it turns out that this is just a product of those weight matrices and in given layers, and diagonal matrices that are defined as having the derivatives of the activation function at the value of the pre-activations at given layers. Okay? So what you want to have is you want the singular values to be concentrated around 1, right? Not to be close to 0 and not to be really large. Okay? And then you call this dynamical isometry. And of course, the strategy to, we all know the strategy to tackle this question. You use free probability to ask what are the singular values of J, or the eigenvalues of J transpose time J. Okay? What you need is also you need the statistics of the pre-activations here. So you use another method to actually know the statistics of these objects. And what Pennington and other did, they showed that for feedforward neural networks, there is a very special case in which when you have the activation function to be a hyperbolic tangent, and the weight matrices initialized as orthogonal matrices with elements taken from the Gaussian distribution with a particularly set variance and mean, then you actually can achieve this dynamical isometry in feedforward neural networks. And this insight, and in fact, they showed that it's not possible for example, for a much more often used rectified linear unit activation function. And this insight allowed them to train orders of magnitude in an orders of magnitude faster way another type of a neural network called a convolutional neural network that had 10,000 layers, so extremely deep. Okay. So now we want to follow their approach and ask the question: is there a special case like that for residual neural networks, or maybe there is something different happening? Okay. So we adjusted this model a little bit, and we add those skip connections that I told you about. So again, each time after you collect your input to a given neuron from the previous layer, multiplying it by the weight matrices and adding the biases, you act upon them with the activation function, but then you add a term which is just the inputs from the previous layer, and this A is just to let us follow the results of that adjustment. Interestingly, this of course this is slightly a simplified model of the thing that is used in practice. But this simple modification in 2015 led to state-of-the-art results on very competitive image classification recognitions. This one at least, and this is another type of competition in machine learning. So again, we ask the question how we can initialize the weight and the bias, and in particular, most importantly, the weights here, so that learning is as effective as possible. And we have the same strategy, except now the input-output Jacobian has this additional term here. Okay. We use some standard techniques. So we have the Green's function. When the eigenvalues are real, their density is given by the Sochocki-Plamelj formula. We will use free probability theory. So for those of you who are not familiar with that, it allows us to answer questions like what is the spectral density of a sum of two mutually free random matrices, and with the S transform here, what is the spectral density for a product of two matrices that are mutually free. Okay, and of course we will use the S transform for the product here. It turns out that what you want to do is you want to calculate the S transform of this matrix Y transposed with the suffix L representing the layers here, like this. You do it by using a trick akin to the quaternarization or hermitization trick. So we introduce a generalized Green's function. In this, we do it in this particular form here, so that again the generalized R transform is defined with Z and X in those ways. And it turns out that the Green's function, which you're looking for, is the off-diagonal term here of this matrix. Okay. You also use the fact that so what we do here, we calculate this for W's that are diagonal. Okay. You use that fact, and what you get, and what you get is the following. So if you have an object which we call a cumulant here, which under some assumptions on the behavior of the pre-activations that I will talk about more later, can be written as this Gaussian integral here with respect to the square of the derivative of the activation function, with Q being the variance of the pre-activations in a given layer. If you define this object, and if you average it across all the layers, it turns out that first, in the large depth limit, and second, if the variances of the elements of the weight matrices, which I assume are Gaussian distributed, are of the order of 1 over n times L, then the S transform of this full J transpose matrix is this object. And as you can see, it depends only, apart from depending on A, under the assumption that A doesn't scale with L, it depends only on this parameter C. Okay, and this is true irrespectively of the activation function. Okay? So what you get is out of S, you get a formula for the Green's function. So basically, for the spectrum of eigenvalues of J and J transpose and does the singular spectrum, a universal one in the sense that it doesn't, apart from depending on this parameter C, it otherwise doesn't depend on other details of the neural network. Okay? So what is left now is to ask the question, what is C? And for this, you want to go back to the signal propagation in the network, and as you see here, C is the average across the layers of the second cumulant, which on the other hand is a Gaussian integral of the post-activation function, which has its argument multiplied by the square root of Q, which is the variance of the pre-activations in the ELF layer. Okay. So under some particular but quite reasonable assumptions, it turns out that those pre-activations can be seen as Gaussian with mean zero, so centered, and what we want to worry about only is this QL. Okay? And just by using this recursive formula and the central limit theorem, we can quite easily derive the recursive mapping of how this QL changes. Okay? So, for example, if we choose the sigmoid activation function, which is defined like this, this recursive formula becomes that, and you can either solve it numerically or make an approximation in the large limit, and you can see here from this plot that this agrees with what you get if you actually send the information through the network, send, let's say, a random vector and a random input vector through the network, and calculate explicitly the estimator of the variance of the pre-activations within the layers. And it's quite accurate. It's accurately describing the real data. Okay? So now that you have both the ingredients, you can get the spectral density, and this is what we do. It looks a lot like the one for the Wishart matrices. Here we see that in particular for this is for the hyperbolic tangent activation function with the same widths of the with the same widths of all the examples here, with a particular variance for the elements of the weight matrices, and what we do here, we basically take a random vector, we propagate it across the layers of the network, and then we calculate the spectrum of the product of the random matrices as defined by the definition of the Jacobian here. And you can see that already for the width of L, you get a very nice comparison to the theoretical plot, and this doesn't change when you go when you increase the depth.
So this black line is Marchenkov +2 for rectangular matrices?
No, sorry, it's not. It's the result of the theoretical derivation I just showed. It's not the same as Marchenkov Astor. Maybe my comment was a little bit misleading. I just wanted to note that it's very similar in some sense, but it's not. It's not Marchenkov Astor. Sorry. Okay. So what you might want to do you might want to control the value of the parameter c, and you see that the lower it is, the more you are getting closer to the optimal situation when the singular values are concentrated around 1. And finally, you can make the same experiment except using a real data set. So here we used the so-called CIFAR-10 data set, which is a data set prepared for the classification problem of images. You take the pixels of the images as input. And what we do here, this time we use different activation functions to show you this universality. And in each